So hello everyone, this is lecture 3 for the atomic physics. In the last lecture we were discussing about the Bohr's model and we were discussing that how the Rydberg constant will change with when we consider the reduced mass, and this is the reduced mass, the multiplication of two mass divided by sum of them. And today we'll see that how to prove this result. And I told you that that's how your Rydberg constant will change, that is means R infinite divided by 1 plus me by mp. So, and for the deuterium, it will be means simply it is a sum of total mass of the nucleus. I mean, this is a general formula. This is the mass of electron, and this is the total mass of nuclei, and this is your Rydberg constant for any finite mass. So, if you wanna apply these results, these are also applicable on the hydrogen or helium, and the lithium means hydrogen-like atoms. So, these helium plus will become the hydrogen-like atom, as it is also having the one electron in its orbit, and lithium double plus means again it is also having one electron in the orbit of the nuclei. So these formulas are also applicable for the hydrogen-like atoms like these, and only change will be this: in place of RHE, means RH there was R infinite for the hydrogen, it is simply 4 RHE now. Means it will be 1 square for the hydrogen, now 2 square for the helium it will become, because inside we know that here for helium it is 2. So 2 square will give you 4 here. As you know, number of protons inside the helium is 2. That's why its atomic number is 2, and Z square will give you 4 here. So now names are also given to the helium series also, and we call it as the first Lyman series, second Lyman series, Fowler series, and the Pickering series. Means n can be anything. If it is coming to the final orbit is 1, then it will be first, and it is 2, then it will be second, and for third it is Fowler, and 4 it will be Pickering series. So you must remember these formulas for the helium also. Now let's discuss what is reduced mass. So I told you that reduced mass means you are resolving or reducing two body problem into the one body problem. Means if you have one electron and the nuclei, now you can just reduce the system to a single particle which is rotating, and that consider your the mass of that particle, and that will explain or just giving the same result what this two system is giving. So from the principle of moment, if we find the center of mass of these two systems, it will be somewhere here. And if this is distance is x and this is a minus x, means complete distance is a. So it will be x, a minus x. So m multiplied by x must be equal to capital M multiplied by a minus x. From here we can find the value of x. Then a minus x simply means a minus this, which you will solve, you will get this. Small m a, m plus m. So you have values of x, a minus x. Now if you want to find the angular momentum of this system, then it will be this distance from here, and for this it will be mvr, means you know the formula. Then it will be m omega r square. If you write in terms of the omega, that is angular frequency of this complete system is rotating. So it will be sum of this angular momentum of this mass m and angular momentum of this capital M. So it will be m omega x square plus m omega a minus x square. So this simply m omega r square, you know the formula. So this will its total sum of these angular momentums. Now we will just substitute the value of x and the a minus x from here. So we already find that. Now after substituting, we can take some factors which can be common out. Means this will be m, capital M omega a square, m plus m square, m plus m. Now this will cancel out this square, and the remaining thing will be mm divided by m plus m omega a square. Now you will see that we are getting a final system, and if we write this as mu, then it will be something which is rotating with the same omega or the angular frequency and at the distance a. So that's why we call it as the reduced mass. Means now these two body can be explained with the single mass, which is mm divided by m plus m, and now it is rotating at the omega. Means now this is your system. Means this system is reduced to this system, which is at a, means this reduced mass is at a distance a, and it is rotating with omega angular velocity, and now that's why we call it as a reduced mass. Means two body problem is reduced to the one body problem. So I hope you got this, and we also can generalize this. Means if you have some frame of reference and there are two particles m1 and m2, and from the origin their position vectors are r1 and r2, then again if you want to reduce the system to a one particle system, then your reduced mass will be m1 m2 divided by m1 plus m2, and this the position of that will be explained by this r vector will be taken from the origin. Means this is the final one body reduced from these two bodies, and r, you know what is, it is r2 minus r1. So that's how you can reduce. We can prove this also. So let's see the proof of this. Now this is your system. So this is m1 m2. Now there will be center of mass lying somewhere here, so we take the vector or the position vector for the center of mass is capital R. So we take now origin at the this point. So if we write the equation, means for the center of mass, that will be m1 r1 plus m2 r2 must be equal to m1 plus m2 r. So we taken it as the origin, so this will be 0, and now we get this equation, and from these vectors we can see that r is nothing but r2 minus r1. So r2 minus r1 is equal to r. So we'll substitute the value of r2 first. From here it is r plus r1 here, and we'll find the value of r1. Then we'll substitute for the r1 and we'll find the r2 from here. So first we write the r2 equal to r plus r1 in place of this, and we will find the value of r1, that will be this. So r1 dot will be this, and again we can find the r2 from here, and it will be this. Now r2 dot will be simply r dot. So why we are finding this? Now for this two body problem we can write the Lagrangian. So what is the Lagrangian? Lagrangian is simply the difference of the kinetic energy minus potential energy. So that will give you the Lagrangian. So Lagrangian of this two body problem will be T minus V, and kinetic energy of this is half m1 r1 dot square, and r1 dot is this. So the square plus half m2 r2 dot square, that will be this, minus the potential energy. Now we will try to solve this, and after in the last this will be taken out, and you can just solve this. This is a basic calculation. In the last you will get this, and now again as we have seen in this case that it is reduced to one body problem, it is this Lagrangian is also resolved or reduced to one body. Means you can see if we replace this by mu, it will be half mu r dot square, that will be mv square. Now we can just means this is your Lagrangian, and this is for the one body problem. So that's why we can say that reduced mass will be m1 m2 m1 plus m2, and position vector of that reduced mass will be r. So I hope you got this, and this is a very generalized case. If you don't know what is Lagrangian is, so you can go and watch my classical physics lectures. There is complete syllabus I have already uploaded. So also you can see some videos on the YouTube about the reduced mass. Then you will get the very better idea of this. So today we will discuss now the questions based on the Bohr's model, and in the next lecture also we will discuss the questions. So let's start with the first question, that is, first line of Balmer series of hydrogen has wavelength 6536 angstrom. Calculate the wavelength of the second line. So this is given. So now we will consider in all the cases the reduced mass, means in the generalized case we will consider. So we won't write R infinite here. If it is given for the hydrogen, we will write simply RH. And 1 upon lambda 1 equal to RH, means this is for Balmer series, means final state will be 2. And for the first means first line, it will be coming from the 3 to 2. So this will be your formula. And this wavelength is given, and we need to find the for the second line. So it will be 1 upon lambda 2 RH, 1 upon 2 square minus 1 upon 4 square. So we don't need to find this RH. We will just simply divide these two equations, and this RH will factor will cancel out, and just substitute the value of lambda 1, and you can find the lambda 2. That will be this. Next is find the wavelength separation of the first member of the Balmer series due to 1H and the 2H. So we need to find the difference between the first member, means first line, from the hydrogen spectrum or the deuterium spectrum. This 2H is nothing but deuterium spectrum. So for the hydrogen first line we can simply see, means from here directly. For the first, it will be this. You can see 309 minus 4 5 by 36, it will give you 36 by 5, and lambda means RH will be in the denominator. So this will be your lambda H. And same you can find for the deuterium also. In place of RH, just take the RD, and that will give you 36 by 5 RD. So this is the same thing, only the RH and RD are different, because we need to consider here the reduced mass also. So to find the reduced means generalize RH or RD, you know the formula from here. We already discussed this formula. R means generalized Rydberg constant will be R infinite divided by 1 plus m by m. So for the hydrogen, RH will be R infinite divided by 1 plus m by mp. So it is simpler mp because one proton is there inside the hydrogen. But for the RD, it will be 2 mp because there is a one neutron and one proton is there. So we'll consider them same. So it will be 2 mp here. So now this is the case, and now you have the RH value and the RD value in terms of the R infinite, and you already know the value of R infinite. And you need to find the difference between the wavelengths. So you need to find the lambda H minus lambda D. So lambda H, just substitute the value of RH here to here and RD from here to here and take the difference. Then this will be your answer. You already know the values of all these constants. So you can find the difference between the wavelengths. Next is, if the Rydberg constant of an atom of finite nuclear mass is alpha r infinite, so it is a general case is given where r infinite is the Rydberg constant corresponding to the infinite nuclear mass. The ratio of the electron to the nuclear mass of atom is. So we need to find the ratio of electron to the nuclear mass, total mass. So we know the generalized formula for the Rydberg constant, that is this. So we need to find this value, and this is given, that is alpha r infinite. So now we have the terms. So just find this value. It will be this equal to this, means this divided by this will give you 1 upon alpha, and m by m will be this. So this is your general value or the answer. Next is binding energy of hydrogen atom electron bound to proton is given in 13.6 electron volts. So we already know this result. The binding energy of the positronium electron bound to positronium is. So we need to find the binding energy for the positronium. So what is positronium is? So for a simple atom, we know there is this nucleus considering means having the protons, and electron is revolving around it. But what happens in the positronium? There is if we call it as this is your lepton, then this is your antiparticle of that, and this is the positive charge and having the same mass, only the charge difference. So this is called the positronium. And now we need to see that if the binding energy of this is 13.6, then what is the binding energy of this system? So for that, we know what is the reduced mass, means now we have the same mass of both these particles. That's why there is a very big effect on the reduced mass. So simply reduced mass will be mm divided by m plus m. It will give you m by 2. So if you find the ratio of mu by m, that will be 1 upon 2. And you know the formula for the energy for the reduced mass, means the generalized case. This is the formula for energy, that is En multiplied mu by m. So just substitute this ratio here. So En is, means generalized En is 13.6, and for the mu by m it will reduce to, means mu by m is 1 upon 2, and n square will give you, means n is just 1, so it will be minus 13.6 divided by 2. So this is your energy, binding energy of the positronium. Now you can also, if in the question they ask you what is the radius, so that will be again n square by z. This is the general radius, and in the reduced mass considered, it will be m by mu. So m by mu is simply 2. So we already find this ratio for the positronium. So that's why the radius will be 0.52 multiplied 2. So this will be your radius for the ground state. And velocity won't change because in this formula there is nothing like mass. So 2 alpha c divided by n. This will remain same. So this is the question which can also be asked inside the question. So you must remember these results also. Let's see the next question. Consider the high excited state of a hydrogen atom corresponding to the large value of principal quantum number. Means n is very greater than 1, and this is the high excited state. So the wavelength of a photon emitted due to an electron undergoing a transition between two such states. So there are some higher states of the hydrogen, and there is transition being there at this n, and transition is like n plus 1 to n. So there is n is very larger than 1, and there is transition from n plus 1 to n. So how that transition and the wavelength emitted by that radiation is related to the wavelength lambda alpha of the k alpha line of the hydrogen. So what is k alpha? So normally we use this notation for the heavy matter, but this k alpha line here denotes nothing but L alpha, that is Lyman's first series. So how this higher transition wavelength is related to this first line of the hydrogen. So we know k alpha is nothing but L alpha. So we know for L alpha 1 upon lambda alpha equal to r infinite 1 upon 1 square minus 1 upon 2 square, means second to 1 transition. So this is your lambda alpha 4 upon 3 r infinite. So whatever take the value here, this factor will cancel out in the last. So you can take a generalized or the r infinite here. Now for the higher transition, so it will be n plus 1 to n. So this is 1 upon lambda equal to r infinite 1 upon n square minus 1 upon n plus 1 square. So we need to find a relation between this lambda and this lambda alpha. So just try to solve this. So we get this result. Now see, n is very large. So first this will cancel out, and 2n plus 1 will give you simply 2n because this n is very large, and n plus 1 will give you n because this n is very large again. So this will give you n4 in the denominator and 2n here. Now this n will cancel out 1, so it will be 2 upon n cube. Now 1 upon lambda is this, and substitute the value of r infinite from here, and you will get the relation between lambda alpha and the lambda. So that will be your answer. Next is hydrogen in its ground state is collided with an electron of kinetic energy 13.377 electron volt. The maximum factor by which radius of the atom would increases. So there is this case that you have an electron, and that is having the kinetic energy of 13.377 electron, and it is collided with the hydrogen atom. So you will see that energy of this nucleus is very large, as in ratio of means mega electron volt, in terms of mega electron volt. So this electron won't affect the nucleus, but see this electron in the ground state, it will be affected, and They are asking that what is the maximum factor the radius will increase. Means some electron is coming and it is hitting this. So this electron can go to the how means how far it can go from this orbit with this energy. So the maximum will be only when this whole energy is transferred to this electron. Only then it will go to the maximum higher state. So let's assume that whole energy is transmitted to this electron. So the ground state energy is minus 13.6. So add this energy to this, and now the energy of the electron will become minus 0.223 electron volt. And with this energy, at which state it can exist with this energy? So we need to find, means the electron will excited. So at which state it will become? So this is the formula for the any state, minus 13.6 n square. So just equate it with the 0.223, and now find the value of n. So n will give you 7.8. Now there is no orbit something like 7.8, so it must be, means it can't reach to the 8th orbit, so it must remain in the 7th. So n must be 7, and now you can find the radius of the 7th orbit. You know the formula for the radius, n square 0.52 angstrom. So put n equal to 7, you will get the radius. So it will reach 49 times r naught radius when this whole energy is transmitted. So this will be the maximum change, by which means this is the maximum factor, that is 49. Next is if a proton were 10 times the ground state energy of the electron in a hydrogen atom would be. Means now proton is becoming 10 times. Normally what is the ground state energy? That is minus 13.6. But if we consider the reduced mass, then ground state energy is nothing but, means in the normal case when the mass of proton is mass of proton. So that is E1 prime is equal to this m upon mp. So this is the general formula, and now mp is nothing but 1836 times the mass of electron. So this will give you this factor. So this is the ground state energy in general case. Now they are saying that mass of proton is becoming 10 times mass of proton. So in place of this, we will write 10 multiply mp, and mp is 1836 times E, mass of electron. So this will give you 18360 here. So now the ground state energy will change to this minus 13.599 electron volt. Now you are seeing that which energy is lower. So we'll see that this energy is lower. So as the mass of proton is increasing, we will see that ground state energy is decreasing, and when it is becoming very large, it will reach to minus 13.6, which is a generalized case when we are considering that the mass of the nucleus is infinite times the mass of electron. Then it will become minus 13.6. So you must remember this result, that as the mass of the nucleus is increasing, it will reduce the ground state energy. So in the next lecture, we will also discuss some more questions. So that's it for today. Thank you everyone.